This is IAQ Radio, Indoor Air Quality Radio, the voice of the indoor air quality industry, with your hosts, Radio Joe Hughes and the Z-Man, Cliff Zlotnick. And now, Radio Joe Hughes.
Good day and welcome to IAQ Radio Plus. This week, we flash back to May of 2010 for an enhanced version of a great show we did with Dr. Andy Persily from the National Institute of Standards and Technology. During this show, we talked about his role at the Indoor Environments Group at NIST, weatherization, the EPA Day Study, and a free document called the Indoor Air Quality Guide, Best Practices for Design, Construction, and Commissioning, and more. Before we get started, let's thank our sponsors. They're the reason we can continue doing the show. Don't forget about after the show, we can continue the discussion at afterthoughts.iaqradio.com, sponsored by First On-Site. Our marquee sponsor is First On-Site at firstonsite.com. Our association sponsors are the American Industrial Hygiene Association, AIHA.org, the American Conference of Governmental Industrial Hygienists, ACGIH.org, the Cleaning Industry Research Institute, CIRI Science.org, the Indoor Air Quality Association, IAQA.org, the Institute for Inspection, Cleaning, and Restoration Certification, IICRC.org. Industry sponsors are AEML Laboratories, AEMLINC.com, Particles Plus, ParticlesPlus.com, TSI Inc., TSI.com, Sunbelt Rentals, SunbeltRentals.com, April Air, April, AIRE.com, Healthy Indoors Magazine, HealthyIndoors.com.
Hello, Cliff.
Hi.
Good day, Dr. Persily. Welcome to IAQ Radio. Thanks for joining us. I'm just curious about your position at NIST. Can you tell us a little bit about, what NIST does and then a little bit about your position?
Sure. I'd be happy to. And thanks for inviting me to join you today. I look forward to the discussion. NIST, or the National Institute of Standards and Technology, is part of the U.S. Department of Commerce and has an overall mission to do technical research and technical support to kind of further the advancement of U.S. industry, to promote the health and security of the nation overall, to provide support to other agencies in terms of their technical questions. We talk about kind of providing the technical infrastructure for measurement, so that if some industry is moving into a new area, but they, some think of semiconductors where they have to measure, the quality of these circuits at much smaller length scales than they've ever had to before. NIST will hopefully anticipate that and do the research so that they can, move forward in their technology development with a reliable measurement technique. And yes, that extends to building performance issues that we're going to talk about today. My job here, I work in the Building and Fire Research Laboratory, which is one of the major laboratories at NIST, where research is done on a range of building performance and safety issues. And if you work your way down the org chart, you'll find me leading the indoor air quality and ventilation group.
Okay. Cliff?
I just wondered, Dr. Persily, whether anyone at NIST knows what time it is.
Well, I do,
Okay.
because I'm looking at the time.gov website. I was checking my watch, which is now about 7 seconds slow, but NIST has a lot of the people, a lot of folks, think about NIST in terms of traditional weights and measures, activities that still constitute an important part of our work, but it's kind of the historical, and there you're talking about the meter stick and the kilogram and all these other measures that need to get standardized. And part of that is measuring time. And, we can, we work with the Naval Observatory and others to kind of keep track of, the absolute time, and then also how people measure, very small time scales for a variety of technical issues that, frankly, I don't understand that well.
Okay.
But if you go to time.gov, you will be able to set your watch and be more accurate than mine.
Thanks. Joe?
I'm looking back through a long list of research projects and papers that you've done over the years, going back into the late 70s even, and then the early 80s. And we've been talking a lot lately with guests about the current push to weatherize homes and to save money and save energy, more so than money even, and maybe help the planet a little bit with carbon dioxide emissions, etc., by weatherizing these homes. I'm just curious, what kind of mistake did we make early on with respect to this weatherization, and how do we avoid repeating some of these mistakes?
That's a good question and very timely. I first kind of got into this field in the late 70s, during the first so-called energy crisis, and I was involved with a research group at Princeton that was doing some of the first work on retrofitting homes, and came up with the concept of house doctors, and I worked with probably the first blower door that was in this country about 30 years ago. And, there was a lot of good reasons to save energy back then, and probably even more so now. Some of the mistakes, I guess, I put them into two categories. One is kind of, jumping into measures before thinking them through. We all heard about folks who, we want to save energy, we're going to nail up some plywood over the outdoor air intake, or we're going to, tighten up the building without regards to what it might do to indoor pollutant levels. And, buildings are complicated structures. Even the simplest house can get, can be fairly complicated in terms of airflow and pollutant movement. So, before you do something, you need to understand what it's going to do for you. And while energy is important, there's a lot of other reasons, a lot of other important performance issues, indoor air quality being one of them. And if you run down the energy savings path without thinking about indoor air quality, you may get burned. Or if you run down and do things in the path of energy and do things that compromise or lead to moisture problems, and your building may fall down, or you may have some serious material issues. So that's one issue, is kind of acting with good intent to save energy without thinking it through. And then the other is, acting to save energy without checking on whether you really accomplished it or not. You can buy and install lots of caulk and insulation, but if it's not installed properly in the right place, you're not necessarily going to get the performance that you expect. So, just doing it is not enough. You got to do it right, and everybody collectively needs to, kind of establish the efficacy of these various approaches. And, that's true today as well. We're smarter. We have more electronics and computers to help us, but hopefully that won't just result in us making mistakes more quickly, right?
Well, exactly. If I've got limited resources, and most people do, I'm curious, should I look at air tightening first or insulation first, or would it be dependent on my building or my home?
Yeah, I think the answer is going to be building specific. And I think it would depend on the age of the building and the age of the heating and cooling system. I don't think there is a one-size-fits-all. I think there's a list of options, and air tightening is one of them, and, insulation level is another. The heating and cooling system I mentioned, the water heating system, kind of look where the energy is going and where it's coming from. And, I guess an educated homeowner can do it, but it does require some familiarity with the technology and the issues to make sound decisions. So, fortunately now there's a lot of well-trained folks out there doing, weatherization inspections and making these recommendations based on pretty sound information. So again, there's really no one-size-fits-all, but I think the important thing is it needs to be based on the specific building and its specific construction and systems and so on.
And you emphasize measurement. Are we? I'm just going to follow up a little on that. The way the programs are currently set up, and I know they vary, state to state and region to region around the country. I think in general we're doing measurement before the, before any caulking or insulation is added. Have you noticed that? Are you aware? Are we doing a better job of making sure people go back afterwards and verify whether or not what they've done has worked?
I really am not that familiar with how the programs are handling verification these days. I'm familiar with some efforts where there's like a blower door test before and after, and that's pretty quantitative, or maybe a furnace efficiency test before and after it's tuned up. It's harder to measure the R value of a wall reliably, but if a qualified person is putting in the installation, that's probably going to be effective. But ultimately, it probably would be better for everyone if there was some kind of an MPG equivalent for a house, which could be based on utility bills or something that could show everybody, yes, this has worked, we've had an impact, but that takes time. You kind of have to go through a heating or cooling season. And I've heard some people talking about some quicker, more clever techniques to kind of get a reliable indication of how the energy consumption has been impacted, without having to wait a whole year. But I think those are still kind of in the works.
So if you had,
as a lot of money is going to get spent to weatherize homes, and everybody wants it to be effective.
It sounds like if you had if you could wave a magic wand and make sure we did this right, you would make sure we did go back at the end of the year and make sure that we, actually made a positive impact.
Yeah, and again, I don't know what kind of verification programs are in place. I'm going to, suspect there's, people are thinking about that and are going to address that issue because, nobody wants to spend all this money, whether it's a government program or a private homeowner, without some good sense that it's going to have a positive impact, because we know we can. We know we can save energy in buildings, so let's do it.
And that has been your experience. You have been able to verify that by doing these things and doing them in the right method, following the right methods, following the right techniques, we have been able to verify we can save quite a bit of energy.
Yeah. Even going back 30 years again, when I first started learning about these things, there was a lot of energy was saved, and sometimes it took some time to because sometimes the thermal defects in an existing home can be a bit obscure and hard to find, but a knowledgeable person with the right tools can't find them. I remember some townhouses, this is in the 70s, I'm going to guess they were built in the 60s or 70s. They made efforts and reduced the energy consumption by 3/4, which is, no reason, that can be done. Now the whole issue then becomes, is it cost effective? How much time and how much money does it take? But we know energy is a lot more expensive now than it was back then. So, it makes sense, from an economic point of view, exactly which measures kind of are no-brainers, which ones, need a little bit more consideration, and which ones maybe, more expensive that can be justified currently. That's a tougher question.
Got a text question, Cliff. Do you want to take that, or do you want me to take it?
No, I can pose it. Doctor, could you describe your experience with the EPA base and the ASHRAE studies regarding ventilation and areas for future research?
Sure. So you're referring to the EPA Day Study?
I believe that's what the text question's about. Yes, it's from a listener.
Yeah. I mean, this goes back, it's probably, it's close to, 20 years ago, EPA realized that most of the buildings that were being studied for indoor air quality issues were problem buildings, where something was going wrong and people were called in to try to figure it out and fix it. And that we, didn't really have a good idea of what a non-problem building looked like. So you go to a building and people were complaining about headaches. Half the people had a headache last week. Well, was that high or low or in between? So they constructed this base study, which was really, very important for the field and is worth looking at. To go out to some buildings, kind of randomly selected, buildings that hadn't been written up in the paper because of lawsuits or IAQ problems, and they went in for roughly a week in each building and measured a bunch of indoor air pollutants, characterized the building, did some ventilation assessments, and then did occupant questionnaires so they could, develop this fairly rich data set of all that information in so-called non-problem buildings. And we were involved, at NIST, we were involved in developing the protocols that were used to do the ventilation assessments of the buildings. How things would be measured and analyzed and what information would be collected. And then subsequently we evaluated the ventilation data that was collected in those buildings. And all this information is available, the whole protocol for these tests and all the data are available on the EPA website for people who might be interested. I think I only partially answered your question, so I'll let you follow up if you.
Yeah, let me do that. We will also, by the way, for any listeners out there, we'll put a link up to that information on the EPA website at the tomorrow after I get back into the office. But I guess the specific question was, first of all, to give us a good background on what the base study was, and that helps quite a bit. But also, they were, I guess, asking, what areas for future research would you, would you propose, or are you already working on future research with respect to ventilation, and has the, have your previous thoughts on the issue with respect to ventilation been confirmed?
Well, in terms of future research, there's a whole slew of issues. And there's been some pretty good kind of research planning efforts that have been put together by EPA and the U.S. Green Building Council and NIST as well, and others. And I could send you information on those, but rather than me pulling those out and reading them. In terms of ventilation research, I think one area that we need is that it's really hard to go into a building and get a good measure of the ventilation rates. What kind of, how much outdoor air is being brought into the building. It's really, fairly tough to do that reliably. And the more complex the building, the more complex the system, the tougher it is. And if there was a way, to, go into a building without, too much technology and, too much time and too much expense, and go in there and get a better number than we're getting today, that'd be great. Whether it's a home or a, commercial building, that's something that's really needed. So we need to develop some more accessible ventilation measurement techniques. I think that's one area. Another that comes to mind is as we, try to both save energy in buildings and maintain, if not improve, the indoor air quality, there's all sorts of good ideas being generated and proposed to do ventilation a bit differently. And some of them, I think, are more well established than others. But we need to take a hard look at some of these different ventilation technologies and, how well do they perform? How should they be designed for a specific building? How should they be maintained so that, the good performance in terms of energy and IAQ continues, for years throughout the building life. So I would say ventilation measurement and then innovative ventilation technologies are two research areas that come to mind. And I'm sure if I thought more or as we talk more, I think others would, come up as well.
I noticed in your papers that there was one on the use of carbon dioxide as a surrogate for determining whether or not ventilation was effective within either residential or commercial buildings. I guess more so commercial. And with how complex they are, I understand a lot of our listeners who do indoor air quality investigations will probably use that. Can you give them some tips on what mistakes not to make, maybe when using carbon dioxide?
Sure. I mean, measuring indoor levels of carbon dioxide to assess ventilation and IAQ, is pretty widely applied and has been for a lot of years, and it has a lot of advantages because CO2 is, among all the pollutants that you might have to measure, is relatively easy to measure. The technology is, not particularly expensive or noisy or heavy or complex. And, you have a built-in injection system for carbon dioxide in a building, namely the occupants. That said, when you use carbon dioxide in this way, you're basically using it as a tracer gas. And, a tracer gas traditionally is a gas that is injected into the building in some controlled fashion, and then you measure the concentration over time, and then you back out parameters of interest like ventilation rates. And when you use a tracer gas, there's certain things you got to do, to get useful information out of it. And just because a tracer gas is carbon dioxide and it's free and it's already there, you still got to follow the rules. So, the most common application of CO2 is to measure the rate and then try to calculate the outdoor air per person. And for that to work, there's a few assumptions. They include, but aren't limited to, that the outdoor air ventilation rate is constant, that the occupancy is constant, and that the indoor CO2 is built up to a steady state level. And those conditions may or may not exist. Without going into a lot of technical detail, carbon dioxide can be very useful, but whoever's doing it needs to understand, what are the assumptions behind the technique, and what are the, what do they have to check for, to make sure they're going to get a reliable value. There's actually an ASTM standard that describes how to use carbon dioxide to evaluate ventilation and indoor air quality, and that standard is D6245. I also have a couple of papers that describe this, and I could send those to you. And since I wrote them as a public employee, they're in the public domain, so they can be distributed, and they don't have perhaps the authority of an ASTM standard, but the technical information is still hopefully pretty helpful. I think a kind of a practical concern with CO2 measurements that I I'm going to assume a lot of your listeners probably realize is, these devices, while, they can be quite good and reliable, they do need to get calibrated. And so that's one key issue is calibration. Another is, the carbon dioxide levels in a building are on the order of 1,000. The air you breathe out of your mouth is on the order of like 30,000. So you need to make sure that the measurements are not influenced by you or other nearby people. And then the third key is that these indoor levels are always with reference to the outdoor level. And outdoor CO2 levels can vary quite a bit over time in geographic locations. They can get pretty high, for example, in an urban area in the summer when there's temperature inversion. So you really need to check the outdoor level as well. And that actually can be a nice way to check out your device, because if you measure it outside and you're getting 1,000 ppm or something very high or very low, that's a quick indication that something funny is going on with the device.
Okay, well, I appreciate that. And guest three, I don't know if I anticipated your question or if you were following up, but if we didn't answer your question, just send us another text if you would. We're coming up on halftime. I know the Z-Man, we've got to sell a little soap and thank our sponsors, and we'll bring Dr. Wow in. But I also want to let listeners know we haven't neglected the Indoor Air Quality Guide, best practices for design, construction, and commissioning. Dr. Persily was steering committee chair on that one, and we're going to talk a little bit about that after halftime. So if you can hang in there with us for just a moment, we'll be right back.
Okay. Our marquee sponsor is First On Site, your trusted full-service disaster recovery and property restoration company at firstonsite.com. Association sponsors are AIHA, Healthy Workplaces, A Healthier World, AIHA.org, ACGIH, Advancing Careers of Professionals in Environmental Health, Industrial Hygiene, and Safety, interested in defining their science, ACGIH.org, The Cleaning Industry Research Institute, see more deeply through science and research, CIRI Science.org. The Indoor Air Quality Association, IAQA.org. The IICRC, a nonprofit standards development and certifying body for the cleaning and restoration industry, IICRC.org. Industry sponsors are AEML Laboratories, free shipping, great pricing, same-day results with no rush fee, AEMLINC.com. Particles Plus, feature-rich particle counters and air quality instrumentation. Count on us, particlesplus.com. TSI Inc., an industry leader in precision instrumentation for monitoring indoor air. Learn how to expand your IAQ investigations, TSI.com. Sunbelt Rentals, availability, reliability, and ease for all your IAQ and restoration needs at sunbeltrentals.com. April Air, healthy home, April, AIRE.com. And Healthy Indoors Magazine, a free online magazine for industry professionals and consumers, healthyindoors.com.
I know Cliff was also interested in the fire side of things, but I also realized you don't do a great deal with that. Can you give us a little bit of background on what the group does there at NIST, NIST with respect to fire?
Sure, it will be brief because I'm not, involved in it, so I try to pay attention because it is interesting stuff. They have done, kind of split into two areas. One, the more fundamental research, which is where they've looked at flame spread and the, byproducts of combustion and fire suppressant technologies. And, I don't know kind of the split, in terms of past work and current work in the area of toxicity, for instance, but I know that's something they looked at. I know they've looked at the performance of, flame retardants and, what that does for flame spread and then what that might do for the, what's released when a fire occurs. And so there's, that side, where they're looking at, kind of the science behind it. And then there's a whole nother area of activity, which is kind of more applications, and it's, building evacuation strategies. How long does it take to get the people out? What's the best way to do it? I know they've been looking at using elevators, to evacuate folks. And while that's been a no-no for a lot of years, when you talk about a big building and you have folks who are, in wheelchairs and other, have other constraints on their ability to move, elevators, may make a lot of sense, if they're, used properly and designed for it. And they look at sprinkler systems and smoke detectors, again, kind of and equipment and technology for first responders. So that's kind of on the practical side. I love conspiracy theories too. I'm not, haven't really followed the energy crisis ones. I kind of like to go out, for the more exotic conspiracy theories. But I guess that'll be another discussion.
Like 90.
Comment. I'm trying to figure out. Yeah, could be, or maybe a different station. But the comment on not being able to figure out where the outdoor air is coming in is really true, unfortunately. And then one interesting finding of the base study, they went to these 100 office buildings, and they were going to look at the amount of outdoor air being brought in. So first they wanted to see what the design level was, how much was the building designed to bring in. And only in about half of the buildings could they even track down a design outdoor air intake rate, which, some people thought that number was high and others were amazed how low it is. But, how are you going to ensure that a building is being operated correctly when you don't even have, design value to which it's supposed to be operated? So it's
great follow-up. And
pretty telling reality.
It's a great lead into what I think was a big part of the reason for the development of the indoor air quality guide here, that you were such a big part of. I mean, was part of the reasoning behind. Well, maybe you could just tell us how did this come about? We've got the American Society of Heating, Refrigerating, and Air Conditioning Engineers, ASHRAE, the American Institute of Architects, the Building Owners and Managers Association, the Sheet Metal Air Conditioning Contractors, the U.S. EPA, and the U.S. Green Building Council, all working together on a best practices for design, construction, and commissioning book. Is part of the reason for developing that to, the fact that we did find we don't know where the outdoor air is coming in from and some other things?
I think that's one of the many problems or concerns we were trying to address with this document. But in thinking, kind of thinking back on this document, this indoor air quality guide that was published earlier this year for the first time, it was a multi-year effort, and I had to think a little bit, why did we start this? And I think there's really two fundamental reasons. The first is, prior to this document, there was, lots of good information on indoor air quality in buildings, that had been developed over the years, various documents, research papers, guidelines, all sorts of things, but there wasn't really a comprehensive collection of this information, and there certainly wasn't a good collection targeted towards the people who designed and build the buildings. We can write papers and we can talk to each other as IAQ experts and consultants and whatever about how to do it right, but to really have an impact, you've got to talk and you've got to communicate to the designers and ultimately to the building owners or the developers, the people who, write the checks and tell the designers, this is what I want in my building. So one goal was to put together, the practical information to the people who need it, so you're going to have an impact. The other reason, the second reason is, that ASHRAE and had spent a lot of time on Standard 62, the indoor air quality standard, first published in the early 70s, and had, been developing that over the years, but the recent versions, the ones kind of starting in the late 90s, were written in a way were written so that they would get adopted by the building codes. Because again, if you want to have an impact, you get it into the building code, because then when the building code is adopted by a local jurisdiction, it has the force of law. Well, if you're going to write a building code, you're kind of constrained to write in terms of minimum requirements, and it's got to be, in mandatory language and enforceable. And what that means is, it has a lot of power, but if you're writing it in the form of a building code, you can't put in a lot of things. You can't put in examples. You can't put in explanatory material. You can't put in some good ideas that aren't quite right for a requirement. So all this good information, couldn't be put in the 62.1. And so ASHRAE early on identified, that there was a need for another document, some kind of a guidance document that could contain all this other good stuff that didn't belong in the standard. And they developed a relationship with the Environmental Protection Agency, who had a long history of developing some pretty solid guidance on IAQ, and that relationship led to the development of this document.
I'll tell you, that really helps me. I appreciate that explanation, because I've been reading through this document. Unfortunately, I haven't gotten to the CD yet, but that's probably where a lot more of the detail is. But it helps me understand better why the document's written the way it is, and there are a lot of great little case studies in here and things that you wouldn't find in a minimum standard. So that was a really helpful explanation. As a part of this document, and we've got a couple text questions that we'll get to here in a minute, but before we go there, as a part of this document, there seems to be quite a bit of emphasis on commissioning. And I just want you to, if you would, tell us what commissioning is per your definition of commissioning, and also, how often is proper commissioning actually done on new buildings in your experience?
That's a good question, an important question. And commissioning, and I'll just kind of give a plain English definition. There's all sorts of documents that have more kind of precise definitions that are important. But in terms of, what does commissioning mean to me? It means, making sure that the building and the systems in the building are, were installed and operate as intended. You can design a great building, and you can even, buy all the equipment and have all the great materials and so on. But, things happen, just in a big enough building or any building, things don't always get put in right. And commissioning is the process where you make sure that the building was constructed and the equipment installed to operate as intended. That's kind of the quick explanation, and that has to do with kind of mundane things like taking the guards off of fans so that they can operate, to making sure the pumps are going in the right direction, to making sure that the flashing around the windows was put in right. And ideally, it's a lifelong process. It begins at the very earliest stages of design so that everybody knows what's going to be checked and how it's going to be checked, and kind of build it into the process so that it's not rushed, and it continues through construction and after occupancy. Some people talk about recommissioning the building, into its life, to make sure that things are still operating as intended. How often is it done properly? I'm not sure anybody knows. It's certainly done more than it used to be, and that's a good thing. And I'm sure there are some commissioning efforts that occur that some folks wouldn't characterize as proper. But I'm not an expert on LEED, but I'm pretty sure that LEED either requires a commissioning effort or at least provides for some extra points if a commissioning effort is part of a building project. And, that's helping, getting it out on the street for sure, and presumably improving practice as well. But it's really important.
Well, I appreciate that answer. That was very much what I was hoping you would say. I kind of figured you would, because I think a lot of people, when they think of commissioning, they think more of just testing, adjusting, and balancing. and not necessarily all the other aspects of commissioning that you mentioned in your answer. So we appreciate that, and kind of leading in from testing, adjusting, and balancing, and also following up on your interest in ventilation. Can you explain for us how buildings should be pressurized? And should they be positively pressurized, negatively pressurized, neutral, or is it going to vary?
Yeah, I mean, it really is going to be situation specific to a degree, depending on the climate, depending on what kind of building it is. I think generally when folks talk about commercial buildings and office buildings, and some institutional buildings, they tend to think about positive pressurization so that, you have less infiltration into the building, but, you have to be a little careful and really, it's a potentially complex subject. And, we've all heard lots of horror stories, particularly in humid climates, where a building becomes depressurized due to some sort of equipment problem or air distribution problem, and then you get the issue of hot, humid air being drawn into the building, condensing it on the first cold surface it sees, and, liquid water and mold and all sorts of problems resulting. So we know, that buildings in hot, humid climates, do need to be pressurized, but just saying, a building's going to be pressurized, I mean, it's easy to say, but in reality it can get pretty complicated because it could be overall it's at a positive pressure, but you could have local parts of the building that are negatively pressurized because of an issue with a particular exhaust fan that serves part of the building. So you gotta look at you have to look at the building as a whole, and you have to look at it locally. And, but when you get to cold climates, too much pressurization can be a problem. If you go back to the 70s and you look at, there's some great stories out of Canada where some buildings were leaky and positively pressurized, so then you have the humidity from inside getting pushed out, hits the cold part of the facade and freezes, and ice expands, and there's all sorts of dramatic horror stories about, concrete panels on the outside of buildings getting forced off the building from this freezing ice and, landing in the street. So it's serious business, but it can be done, correctly. It's more straightforward if you're in a real hot, consistently hot and humid climate or consistently cold climate, but there aren't a lot of those. There's a lot of back and forth climates that spend time in both realms. So you need to give it some thought, and there is some good guidance on that. And that's something that's discussed in the IAQ guide. And I feel like I'm going on a little bit, but I'll just mention that, for some particular spaces, they require special attention. Like, if you have an indoor swimming pool, you want that to be negatively pressurized relative to the rest of the building so that the moisture and any treatment chemicals don't get into the rest of the building. So there's also kind of local or space-specific issues that you need to deal with in some buildings.
We talk a lot about positive and negative pressurization, but I guess if you could maybe help explain for, and I know it could take a while, so I'm not sure if you can do it quickly or not, but how do we do that? How do you keep a building in a hot, humid climate pressurized positively so that it's not and it's consistently pressurized positively, not just during certain times of the day or during certain seasons or whatever the case may be? What are some of the best techniques, or is there one maybe you could talk to us about?
Yeah, I think there's a range of issues that need to be looked at, and kind of I'm just going to start with the envelope construction. Even if you do a very conscientious design to positively pressurize the building, there will be periods of time where your system may not, due to weather conditions or something, may not kind of do, perform quite as well as you'd like it to. So you have to design the envelope so it can tolerate some wetting. It has a way for the liquid water to drain out and for wet surfaces to dry out. So I start with an envelope that can tolerate, some of the moisture that invariably, occurs. And then, then you'll just, at a gross level, you look at how much air is coming into the building through the ventilation system and how much is leaving, through the exhaust system. And don't forget the local, the toilet exhaust. And you just kind of do a net airflow balance. And if you want it to be positive, you better be bringing in more than you're taking out. And think about that not just at design conditions, but at part load conditions and, other conditions of operation that your system is, or your systems, on a whole building scale are going to have more air coming in than leaving. And then, you probably go down, to local scales and think about, duct leakage. And, a good example that people have talked about quite a bit are using plenums as exhaust ducts. And as soon as you do that, you have a negatively pressurized space, even though the whole building may be positive on average. And so you need to think about, am I creating negative pressure zones without thinking about it because of the way I'm distributing the air or pulling out the exhaust air? So you need to think about those local effects. And, you can get into some sophisticated controls that are going to monitor the pressure difference and adjust the fan speeds or damper positions to maintain the positive pressure, but that can get, it can get complicated, and probably isn't always, isn't needed in all buildings. It's a whole other layer of complexity in terms of commissioning and maintenance and operations. So, maybe everybody's better off, to kind of start with the fundamentals, and in situations where it's really critical, maybe you do need to get into real-time control, but that might not be where you want to start.
I think that's a great, it really helps me, start with the envelope and make sure that it's tight, but also that it can dry out, and maybe not worry so much about the pressurization as I guess sometimes we're led to do. Now, that, you talked about this pressurization issue, and it kind of ties into a question that's been texted in from one of our listeners here, and they're asking if we should do more direct measurement to determine ventilation rate. And I guess maybe I could add to that. I assume they're talking about direct measurement of the outdoor air coming into the building through measuring the amount of outdoor air as opposed to using a carbon dioxide. But also, if you could maybe kind of compare that, and also going to the level of using a tracer gas.
Right. And I think the issue here is real-time control of outdoor air and real-time measurement to verify that you're bringing in the required amount all the time. And that's, that may be the Cadillac approach, and in some situations it's probably called for. But it is an extra level of sophistication and cost and maybe even complexity that you may not need. For a system, a simple constant volume system that's well maintained, you probably don't need to do it. But if you really want to know, you have to measure it. And there are more and more sensing systems coming onto the market to measure outdoor airflow rates, not based on carbon dioxide, but based on, some sort of a pitot principle or some sort of a pressure drop device in the dampers or somewhere else, or some kind of a hot wire system. And, those can be used, and they can give good numbers as long as they're installed properly. And that's really a design decision about whether you need it, but if you want to know, you got to measure it. Tracer gases are largely a research tool. I couldn't see that being used kind of routinely in a building to kind of continuously monitor air change rates, except in a research study. And again, because that's a whole nother level of complexity and sophistication and cost. It's probably hard to justify, maybe on a periodic basis in some types of facilities, but probably not most commercial buildings.
Okay, let's make sure our listeners know that we talked in advance to Dr. Persily about maybe sticking over for an extra 5 or 10 minutes. So I know we're getting toward roundup time. Cliff, did you have anything you wanted to add? And I will get these other text questions in during the roundup there. So hang in there with us, folks on the line, or if you can download the show later. We're going to go a little over today. Cliff?
Yeah, actually, I just had a couple, and what I'll do is if I do them both now, I don't need to ask one during the roundup. I guess in looking through some of the research papers that you've done, there were two that caught my attention. I'd like to know what is a gas phase air cleaner and whether or not this type of device would be beneficial to indoor air quality.
Sure. A gas phase air cleaner is a device to remove gaseous contaminants from the air. I think folks are more familiar with particle filtration, which are, media filters or electrostatic air cleaners that take out particles. And these gas phase air cleaners take out gaseous contaminants. And so that's the distinction. There's a number of technologies. People are probably familiar with activated charcoal. There's other sorbent materials. There's, kind of out there closer to the cutting edge, there's some photocatalytic approaches. And, if you want to take out gaseous contaminants, you need some technology that one of these technologies to do so. And they're used in some applications. I've heard of them in museums where they've got to control, certain contaminants to protect the artifacts, or in some industrial facilities where they're, trying to keep corrosive outdoor pollutants from, attacking electronics that are controlling these industrial processes. So they're out there, and, they're more expensive, than some people may feel they can justify. One key issue, though, is that for particle filters, we have standards and ratings, these, MERV ratings, and I assume most of you folks know about, where you can say, I need a MERV 10 filter, and pretty reliably that it's, been tested, and its performance. We're not quite there with gaseous air cleaners yet. We don't have the rating methods quite in place. ASHRAE is working on some, and have made some advances there, but that makes it tougher to design these systems and specify them until those rating standards are, developed and approved and on the street.
Okay. I guess my second question, again, there was another paper that you wrote, and I'd like you to tell our listeners, how do stoves and toasters affect indoor air quality?
Oh, okay. Yeah, we've recently done some work looking at particles generated, very small particles, generated by normal household activities. People have been measuring indoor particle concentrations for years, and as well as outdoor, and outdoor levels are regulated, as you know. But, people have found that the health effects seem to be more serious as you get to smaller and smaller particles. And there's a fellow retired from EPA, Lance Wallace, that hopefully are familiar to some of you, who's done a lot of work in this area. And we worked with him where he was looking at very small particles in residential settings, generated from cooking and candle burning and, vacuum cleaner operation, pretty mundane activities, and seeing a lot of particles generated. And then as time has moved on, the measurement technology has advanced where we can measure smaller and smaller particles. And now we're getting into the nano range of just a couple nanometers diameter in some of these particles. So we did some work with Lance to measure the nanoscale particles released by cooking and so on. There were an awful lot of them. And in terms of number and in terms of surface area, they really dominate the big particles. Now, how that relates to health effects is a whole other issue that, needs to get sorted through by the medical folks. But, just cooking, toasters, and so on generated, quite a bit of these small particles. And, it was a pretty interesting finding. Some folks wanted to call this the killer stove study, but we weren't quite comfortable with that because this is not a new source of pollutants. We've been cooking in homes for centuries and longer, but there's some interesting work to be done, regarding the particle generation by cooking and other residential activities.
Was there one type of stove that was worse than the other? Was gas or electric?
We only looked at one of each, so
Okay.
I think it'd be, you wouldn't really say on a general basis that one's worse than the other, but they probably, we did some tests without cooking anything, just running the stove.
Mm-hmm.
And so the nature of the particles is likely to be different. We think for just gas combustion, you're seeing soot precursors and other types of particles. And the electric stove, from the elements, the particles generated there, we're not entirely sure what they are. We're trying to develop methods to collect those particles and then analyze them to determine what they're made of and, kind of where they come from. Because, we don't really know, are all particles, are the smaller particles a health issue because of their size or because of their shape or their composition? And nobody really knows that yet, and we need to dig into this a fair bit deeper, and we hope to be doing that soon.
Fascinating stuff. Back to you, Joe.
Okay, I guess we're in roundup time here, Cliff. I don't know, Herb. I'm at Herb Lehman's office here, and I don't think he's used the NIST clock. His clock's saying 101. My watch is saying 106. So maybe we better round up.
The Roundup is brought to you by April Air, providing healthy humidity, ventilation, and air purity solutions for new and existing homes. April Air, healthy air, healthy home at aprilaire.com.
I've got two quick questions if we can keep you on for another couple minutes here, Dr. Persily.
Sure, no problem.
Great, I appreciate that. I guess the one is not even so much a question as a request from a listener for you to maybe pitch what is referred to as contam. Can you tell our listeners what that is and maybe give them some information?
Oh, sure. I should do that every chance I get. Contam is a public domain, meaning free, software tool to calculate airflows and contaminant levels in buildings. And I could give you the website now, but it's probably something you can follow up with, probably better with some of these various documents. But basically, it's a program where you enter some information about a building, and then you can calculate ventilation rates, you can put in contaminant sources, and calculate concentration profiles. Now, there's definitely a learning curve, like all software, even word processing programs, right? But, once you kind of get comfortable with it, it's pretty powerful, and you can account for all sorts of sources and filtration mechanisms and mechanical ventilation and so on. So if folks are interested in having this tool to do some of these calculations, I'll get you the website and I'll assume you guys can post it somewhere, and I wish everybody good luck and good calculations using it.
Well, we can do that. We'll put that on our we'll put it on the homepage for this week, and then I'll move it over to the resources page after the next show we do in 2 weeks. Before we go, I got a quick question, and then if you want anything you'd like to add before we go, that would be great. But I'm curious, what do you think? I'm looking at all these different indoor air quality issues, and obviously mold got a lot of attention early in the 2000 era here. What in your mind? What's the thing that we should really be looking at as maybe the next big thing on the horizon with respect to indoor air quality issues?
That's a really good question. I've never claimed or proven myself to be a very good prognosticator. I think the next big issue is I'm going to say that it's really the current issue is kind of reconciling the push towards energy efficiency or even net zero buildings and maintaining or even improving indoor air quality. I think a lot of people see energy efficiency and indoor air quality as in opposition, but there's a whole lot of ways you can get both without spending an arm and a leg. And I think that maybe it's not a research issue, but an application issue is how can we move forward, reduce energy consumption in buildings, at the same time, improving the indoor environment. And I think there's lots of opportunities to do that, and it's just going to take, some dedicated folks, to commit and move forward.
All right. Before we go, first I want to thank Dr. Weil for joining us today. We're running low on time. I knew this was going to happen when we had you scheduled, so we planned a little in advance. We'll bring Dr. Weil back in 2 weeks here when we come back. But before we go, is there anything that we missed that kind of sticks out that you'd like to add?
I can't think of anything. This is you had some good questions. Hopefully I had some fair answers, and there's lots more to talk about as you know.
Well, you did a wonderful job. We really appreciate having you on. I encourage the listeners to grab a copy of the Indoor Air Quality Guide. I've got a list of about 10 more things that I wanted to touch on that we obviously didn't have time to do. And I think one of the things I'd like to talk to you again about in the future is these advanced ventilation approaches that you discuss in the back of this book. Well, in the last chapter anyway. And
I'd be happy to do that.
We really appreciate you joining us this week on IAQ Radio. Dr. Andrew Persily from the National Institute for Standards and Technology. This is Radio Joe Hughes saying thanks to all of our listeners. I want to thank the Z-Man, Cliff Slotnick, Environmental Annie Kowalicki back at the station there for handling the controls. Of course, our technical director, Dr. Dietrich Lau. Most importantly, our growing group of loyal listeners. Guest 5, thanks for those great questions. We'll be back in 2 weeks. We're going to take next week off for the holiday, and we'll see everybody back here in 2 weeks for the next edition of IAQ Radio.
For IAQ Radio, I'm Spike Reel saying thanks for listening.